Hi students. In our last class we have been dealing with the basic concepts of network security. Today we will be dealing in detail about symmetric encryption. So what is symmetric encryption? As the term suggests, it means a single key or a secret key encryption method is used here. This is the most conventional type of encryption method. What do you mean by symmetric? Symmetric means same. That is, both the sender and the recipient is sharing the same key. So there is only one key which is being shared by both the parties. In that case, such type of encryptions can be termed as symmetric encryption or single key encryption or secret key encryption. Okay, now let's see the important ingredients, the key ingredients of symmetric encryption. There are mainly 5 important ingredients in this type of encryption. The first one is plain text. Plain text is the original message which is being fed into the algorithm as input. The normal message which we write or the normal message which is to be sent over the communication channel to the other end. So this is not encrypted yet. It is the form, it is the message in its original form. So that original message which is being fed into the algorithm as input is called as the plain text. So that is the first important part. The second one is encryption algorithm. Here the plain text is now transformed to some other form which is not easily readable by an third party or by an opponent. So some encryption algorithm must be used to scramble them or to reshape it. So in that case, the encryption algorithms, most of the algorithms may be using the process like substitution and transformation. It's very important to know what is substitution and transformation. Substitution, as the name suggests, each bit in the word or the message is being mapped with another. Okay, and in transformation or transposition, the letters or the bits are rearranged. Okay, so in substitution method, each bit in the message is mapped to some other bit, and while in transformation, the bits in the message are rearranged. So certain processes are used in different encryption algorithms. So first one is the plain text, second one is the encryption algorithm. The third one is secret key. Yes, secret key is one of the input that is being fed into the algorithm. That is, actually this transformation, substitution, etc. is making use of this secret key to move to the next section. So secret key is also one important input that is being fed to the algorithm. The fourth important ingredient is ciphertext. Ciphertext is the scrambled message which we get at the other end. So the message is now being encrypted form which is not easily read or understood by a human. So that form you call it as the ciphertext. Okay. Now let me say something about the ciphertext. It's nothing but for the same plain text, if two different keys are used to encrypt it, and you will obtain two different ciphertext. That is, one key for a plain text will generate a different ciphertext, and another key for the same plain text will give another ciphertext. So based on the keys, the ciphertext will also change. The fifth most important ingredient of this symmetric encryption is decryption algorithm. Now the data is, or the message is in scrambled form, which is not easily understandable by human. So it must be converted into a form which is being understandable by the human. So that conversion, actually the reverse of encryption, is the decryption process. So what happens in decryption? Our ciphertext, which is the scrambled message, is the input here. It uses the same secret key which is shared by both the sender and the recipient. It uses the same secret key to obtain the plain text as output. This plain text is the same as the first plain text. Let's see a model for symmetric encryption. Here plain text is taken as the input. Let it be X. Some encryption algorithm like AES is being used. This algorithm is using a key which is shared by both the sender and the recipient. So using that key you get the ciphertext. This is a ciphertext transmitted area. The scrambled message you get here. So you can write it as a function like, let CT means ciphertext is Y, let it be. So in that case Y will be obtained as a encryption function where the inputs are the plain text X and the key K. I hope it's clear. Here we write Y is the ciphertext. Ciphertext, let it be, we obtain by encrypting or encryption process where X is the input and also the key is another input. Okay. Now you have the ciphertext, transmitted ciphertext over here, which then enters to the decryption algorithm, which is actually the reverse of encryption algorithm. Here also the same secret key which is being shared by both the entities are used. So the key is being used in this decryption algorithm. And finally you get what? The plain text at the output end. So the plain text at the output end can be again written mathematically as, we have already said the plain text is X. So X is equal to, now you have encrypted, now you have to do the decryption process. So the decryption process will be done for the ciphertext as well using the key K. So now you are aware about the concept symmetric encryption. Both the parties, the sender and the receiver, is sharing the same key. So how can we now say a symmetric encryption is secure? So we have to be aware about the requirements for secure symmetric encryption. Actually, the requirements can be classified just into two. A strong encryption algorithm is important here because the data, the original message should be scrambled in such a way that it is not very easy for the cracker to crack it. So a strong algorithm is very important requirement. The second most important thing, or second important requirement for a secure symmetric encryption, is the secret key distribution. We have already said the secret key is the same for both the ends. So it should be distributed very safely and securely, and this is yet another important requirement. Now let's see the term cryptography. What is cryptography? What is cryptography is nothing but it can be defined in three different dimensions. The first one is the types of operation for transforming plain text to ciphertext. So all the basic encryption algorithms are based on two main principles. The first one is substitution, the other one is transposition. We have already dealt with the concept. What is substitution? Substitution is nothing but the bits in the message is mapped with another bits, whereas in transposition the bits in the message is being rearranged. So these two important principles are a base for most of the encryption algorithms. So we have to be very careful about one thing, that all these operations must be reversible. That is, I divide the main input into so many parts, subparts, but at last when I combine all these subparts, I am supposed to get the initial input as it is. That is, whatever transformation you do to move from plain text to ciphertext, that's not a problem here, but make sure that no data is being lost. No data loss should happen. Okay, so all the operations must be reversible. So at last when I combine all the subparts, the initial input must be the same, or in short you can say you have a plain text in the input and also a plain text at the output end. Both must be same, exactly the same. No modification should happen. So that is first dimension in which cryptography can be explained. Second one is based upon the number of keys used. We have already said if the same key is being used by the sender and the recipient, such type of encryption can be called as symmetric, or conventional or single encryption or secret key encryption. Can be single key encryption also. At the same time, if both the parties are using different keys for one end encryption and the other end for decryption, if they are using different keys, such type of encryption and decryption techniques are called as asymmetric, public key or two-key encryption. So that is based upon the number of keys used. If a single key is used by both ends, it's symmetric, else it's asymmetric. The third dimension in which cryptography can be explained is the way in which the plain text is being processed. That is, in our previous diagram, we have said that the plain text is given as the input to the encryption algorithm. So the way in which this plain text is being processed by the algorithm is what matters. Actually, there are two ways in which it can be processed. One is the block cipher, the other is the stream cipher. Stream cipher is just like the data is being sent continuously, so the data will be transformed to the output or transformed to some other ciphertext form bit by bit, because it is being sent continuously. Stream cipher, a stream of data is being sent, so the conversion is done bit by bit. But the other case is for block ciphers. The data is being sent as a block of data, so it's a group of characters, so the output will also be another block of data corresponding to the plain text. I'll repeat. So this is the third dimension. Here we are talking about how the plain text is being processed by the encryption algorithm. So it can be in either ways, like one is the block cipher, the other one is stream cipher. In stream cipher, it's continuous data. So as the data is long, how much it is being transformed like bit by bit. Whereas in block cipher, the data is being transformed block wise, so one block at a time. So what is a block of data? It's a group of characters. So for a corresponding block of plain text, another corresponding block of ciphertext will be obtained. So based on these three dimensions, the term cryptography is clear. Our next topic is cryptanalysis. The cryptanalysis is just a process that is being used to discover the plain text or key. So it's an attempt to find out the plain text as well as the key. So the person who tries this or the person who does this process can be termed as cryptanalyst. Okay, so the process is called as cryptanalysis, and the person who does it is termed as or called as the cryptanalyst. So the strategy the cryptanalyst uses based on the encryption scheme that is being used as well as what information is available to him. For example, let's see here. These are just two examples of attacks that can be seen on the encrypted information. So let it be the first attack, let it be ciphertext only. So that is the type of attack, and what information is available to cryptanalyst is the encryption algorithm, the prime process, plus we have already said the ciphertext only, plus the ciphertext is known to him. So with this two information, he will be trying out to figure out what the plain text is, what the key is being used for transformation. Clear? Let's see another example. Here, known plain text, that is the name of the attack, known plain text. So what data or what information is available to the cryptanalyst is the prime process, the encryption algorithm, plus the ciphertext, plus we have already said known plain text. So one or more plain text ciphertext pairs with keys. So with this much information, that is the encryption algorithm is known, the ciphertext is known, as well as some part of the plain text is also known. So it's easy, quite easy for the cryptanalyst to get the remaining plain text as well as the key that is being used for the transformation. So in general, you can say the cryptanalyst, he uses different strategies for different process, because it depends upon, mainly depends upon the information that is available to him. So based on that and based on the encryption scheme that is being used, the strategy used by the cryptanalyst also varies. Now let's see another important concept, computationally secure. it was a previous university question. How can we say, or what do you mean by computationally secure? You are saying my encryption algorithm is computationally secure. What do you mean by it? So it's simple. Two main criteria, or the ciphertext, the other end, the scrambled message. The ciphertext is expected to follow one or both the criteria. In that case, you can say the encryption algorithm or encryption scheme which I have been using is computationally secure. Clear? So what do you mean by computationally secure? Means the ciphertext or the scrambled message is expected to follow any one of the following criteria or both the criteria, so that you can say the encryption scheme is computationally secure. The first one is the cost of breaking the ciphertext must exceed the value of encrypted information. The cost of the financial matter. So the cost of breaking the cipher should exceed the original value of the encrypted information. That is one criteria. The other one is time required to break the code or break the cipher should exceed the useful lifetime of information. See, the opponent, he is trying to obtain the information for some or the other purpose. So he is having a time span for that, or the lifetime of the information might be like, there might be a bound for that. So it's the duty of the, or the aim, you can say the aim of the cracker or the, you say, cryptanalyst, to crack the code as soon as possible or as fast as possible. So in case of computationally secure algorithms, the time required to break the code will be very high. In that case, you can say it exceeds the useful lifetime of the encrypted information. In that case, the time taken is more, and even if he tries to crack the code, there is no use because the time span or the lifetime has end for the corresponding encrypted information. Okay guys, now let's see our next topic, that is Freestyle cipher structure. This was formulated by Horst Freestyle of IBM. Now we have known about the block ciphers and the stream ciphers. So this Freestyle cipher structure is typically designed for block ciphers, especially for symmetric block ciphers. So all the algorithms which have this common logic uses this common Freestyle structure. So when I say Freestyle cipher structure, we should be aware about how the structure is. Let's see. There are various steps in designing the Freestyle structure. Let me just show you how the diagram can be drawn. You have the plain text or the original message as input on your sender side, right? So the plain text is actually divided in two halves, the left half and the right half. Some function, based upon the algorithm we use, based upon the encryption algorithm we use, some round function or some function can be applied to this right half. So we know the algorithm uses a secret key, right? So that key is being used in this function on the right half. So some round function f, which is denoted as f, is applied on the right half, which uses the key. Now the output from that is XORed with the left half to get the new right half, and the new left half is the old right half. I'll repeat the steps again. You have the plain text. It's actually divided into two halves, the left and the right. Some function is being applied on the right half along with the key that is being used based upon the algorithm, and the output from that is XORed with the left half to get the new right half. So actually now the new left half is free, right? So the new left half is the old right half. Clear? So till here it is actually one round. This continues as much as you need. Freestyle structures number of rounds is 16. 16 rounds is the optimum number of rounds that is being used in this structure, 16. So here let's see the steps again. The plain text is divided into two halves. some function is being applied on right half based on the algorithm. This function uses the key K1, K2, K3. For the first round, the key used will be K1. So till the last round, that is 16th round, the key will be K60. This output is then XORed with the left half to get the new right, that is in the second round, and the new left half is the old right half. So these 5 steps are the basic steps that is to be remembered while designing a Freestyle structure. This is the common logic. Now let's see how the security can be measured in such structures. There are just 2 concepts or aspects you can say. One is the number of rounds. As the number of rounds increases, the complexity is being increasing, right? So the one is the number of rounds. Second one, the number of keys. As I have already said, in the first round you use K1. Second round you are using K2. That is a different key. The keys are not repeating. If you have 10 rounds a total of 10 sub-keys are generated from the main key. So the toughness or the resistance to cryptanalyst is high. Okay, so the security can be measured in 2 ways. One is the number of rounds used and other is the number of keys used. Now moving on to a typical Freestyle encryption, let's see this diagram. You have the plain text input which is being divided into a left and a right half. So you have seen, you can see like LE0 and RE0. It's nothing but LR represents the left and right, E represents the encryption. Okay, so this side moving from top to bottom is the encryption. The other side is like LD, RD and all, that is left decryption and right decryption. And make sure the direction is from bottom to top. Clear? So what we are doing in encryption, exactly the reverse happens in decryption. Clear? Okay, so LE0, you can see a suffix 0, 1, 2, 3 and all. That's nothing but for the ith round, the halves will be LE I minus 1. For ith round, the halves will be LE I minus 1, RE I minus 1. That is for first round, it is LE 1 I minus 1. So 1 minus 1, 0. LE 0 and RE 0. That's for the first round. Similarly, when it comes to 16th round, it will be LE 16 minus 1. That is 15. Clear? So let's see how the process is. So now I hope you know the basic concept. So we are doing some round function or some function. We are applying it on the right half. The output of that function is being XORed with the left to get the new right. The new left is the old R. So the same process is going to be repeating whole 16 rounds. Let's see. So you have the plain text input. It's divided into LE0 and RE0. You are applying a function to the right half. So RE0 applied a function, and I have already said for different rounds the keys are also different. For starting with the first round, the first key will be K1. For the 16th round, it will be K60. So let's see, K1 is applied on the function. You get an output, right? That output is XORed with the left half LE0. And when you XOR both that outputs, you get the new RE1. That is the new right side. New right half is RE1. Now it's 0. Now we have turned to 1. And the new LE1 is the old RE0. Clear? So this repeats till 16 rounds. So I have written etc, etc. And let's see what happens in the 15th round. Okay, the second last round. Second last. So in L15, hope you understood the process. You have the inputs and it have now become its 15th round. So the inputs will be, halves will be LE 50 minus 1, that is LE 14, and RE 50 minus 1, RE 14. So we have LE 14 and RE 14. The function, the key will be this 15th round. So the key will be K15. You have applied some function, you have XORed with the LE 14 to get the new right half. The new right half will be, it's like 14 over here, so now it's 15. and the new LE50 will be the old RE40. Got it? Yes. And this continues one more time because this is just the 15th round. I said there are 16 rounds. So in the 16th round, what happens? You can make sure in 16th round, the halves will be LE60 minus 1, 15. RE60 minus 1, that is RE50. Yes. You have a function that is applied on the right half with the key. This is 16th round, so it's the K16. And it's XORed with the LE15 to get the RE16. Okay? And the new LE60 is the old RE50. Now, till here, actually, the substitution has been occurred. Actually, the substitution is occurring on the left side. Have you noticed that? We have already termed two important encryption algorithm principles. What are they? The substitution and the transposition. It can be any permutation or something. So, substitution and transposition or permutation are the basic process that is happening in this Freestyle structure. So, where does this substitution happen? In the left half. And this substitution is implemented by applying a round function on the right half. Clear? Because see, LE was over here and the next left is actually substituted with the right side. Okay? We have already said what is substitution. One bit is mapped with another bit. Okay? So, that mapping is happening here, which means substitution is occurring on the left hand side, which is implemented by applying a round function on the right half. Clear? Yes. So finally we have reached our LE16 and RE16. Now what happens is that a permutation, a rearrangement occurs here. What do you call as the transformation, transposition or something. So the permutation, a rearrangement occurs here. So the LE16 now becomes RE17 because it's no more 16, right? The next one, next number should be taken. It's not the next round, but the next number. Now LE16 have been interchanged to RE17 and RE16 have interchanged to LE17. So till 16 rounds substitution have been occurring, and ultimately after the 16th round what happened? A permutation, a rearrangement happened, and ultimately you get the cipher text, which you call the output, that is the scrambled form. Now the data is being encrypted from the plain text form. It has been encrypted to some other form using all the substitution, transpose and permutation. Clear? Now let's see on what happens in the recipient end. What's going to happen at the recipient end? Just the reverse. Just the reverse means the functioning is very similar and very same, but what is going to happen is exactly the reverse of what happened in encryption is going to occur here. Clear? Let's see. So now we have the scrambled message output in this side, which will be served as the input on the decryption end, right? For the recipient, now the scrambled message is the input. It has to be transformed to a plain text that is readable. So that should be the output at that end. Let's see what happens. You have a cipher text, which is the input over here. Let's see. To start with, you have the left half and the right half. I have already said the direction is from bottom to top. So you have the left half as LD0, left decryption 0, the first one. So for the first round, it will be, as said before, what happened? For the ith round, the halves will be LEI minus 1. Here it's LDI minus 1. So for the first round, it will be LD0 and RD0. And actually, what are the values? The interchanged values are the values here. Okay? That is, the left half will be the right half of the encryption side. That is, on the right half, it was RE16. Actually, that is the left half. On the right decryption end or decryption half, you have the left encryption LE16. Clear? The interchanged values are written there. Clear? This is the case of first round. So moving on, what happens? As said before, the round function is applied on right half, right? Same as here, the round function is applied on the right half. So here also a function is being applied. I have said it's a first round. I have already said this is a reverse of encryption. So which key should be used there? 16th key, K16, right? For the first round, the key used will be key K16. Then only you can decrypt the message as it is. Exactly the reverse should happen so that the message is retrieved as it is. Clear? So K16 is used with the round function, and the output is XORed with the left half LD0 to get the new right half RD1, which is actually the number will be decrementing, right? Now it's LE16, now it has become LE15. And what happens on the new left side will be the old right half. Okay, the old right half will be RE15 because it's decrementing, it's going back. It was just like ABC, now we are going like CBA. Then only the data will be retrieved at the other end. The same process, this is a case of first round. This is the same process going on, etc., etc. It is going on till the, let's see what happens in the second last round. The second last round is like 15th round. So it's one thing is very clear, when the 15th round occurs, it's the second last round, which key should be used? K2, it's the second last. So K2 will be the key used. Let's see the outputs. Here the halves will be, it's 15th round, so the halves will be LD14 and RD14, which is the interchanged values L and R2 because it's the second last round. Function is applied, or round function is applied on the right half. K2 is being used. The output is XORed with the left half to get the new right half, and the new left half will be the old right half. This is being repeating again and again. See, the interchange value has become decremented. Now it becomes like LE1 and RE1. Okay. Now what will be the case with 16th round? The same thing is going to happen. At the 16th round or the last round, the key will be K1. Okay, K1 round function applied on the right half, and finally you get the new right half, and the new left will be the old right. Okay, all that things is going to be the same. The key is K1, everything is done. And finally when you get there, as we did here, that is in encryption, a final permutation you have done, right? The same permutation happens there also. In that case, they will be interchanged, and finally we are going to get the plain text in its original form. So that is our output. That is the readable form for a human. So when it's permuted or some permutation process happens, it is just exactly interchanged. That's all. So the new RD17 becomes the LE0, which is the starting left half. Did you notice? Yes. You have to obtain the left and right as it is at that end. That's all. So you have LE0 as the RD17 and RE0 as the LD17. That is our output or plain text that is to be obtained at the recipient end. That is the plain text original form which is to be obtained at the recipient end. That is the readable form. See? Now let's check the parameters of a symmetric block cipher. So while you design a symmetric block cipher, what all things should be kept in mind? That's that. Okay, so these are the design principles, or you can say the parameters while designing a symmetric block cipher. There are actually 4 or 5 points. That is just the block size, key size, the number of rounds, and the sub key generation algorithm, and the round function. So block size. So it can be like, block size can vary from one to another, but as the block size increases, the complexity also increases, right? So what is our aim? Our ultimate aim is to tighten the security. So we should be more resistant to cryptanalysis, or we must be more resistant to the cryptanalyst. In that case, to tighten the security, we must increase the block size. The standard block size is 128 bits, and same in the case of key size. If you are using a small key, it might be easy for the opponent to crack it. So the key size standard is also 128 bits. Number of rounds. As the number of rounds increases, the security is being tightened, right? The complexity is being increasing. So it increases our resistance to cryptanalysis. So just remember, the rounds must also be more. An optimum number can be like 16 rounds, which we have done right now. The Freestyle structure, it is using 16 rounds of for encryption, and same for decryption also. The next criteria is sub-key generation algorithm and round function. That is nothing but from a particular key or from a main key, we are generating a lot of keys. That is, for 16 round in our algorithm which we use right now, there are 16 sub-keys. So the number of keys is being, or the number of sub-keys that is being generated is high. So there should be a very good algorithm for this. Okay, remember, the algorithm which we use is not kept secret, but the key which is being used is to be kept secret. So the secret key must be as tightened as possible. Clear? And the same as the case of round function also. All these criteria actually increases the resistance of algorithm to cryptanalysis. So it makes the opponent tough or difficult to crack the code. That's it.